Hello, everybody, and welcome to Torque and Drag Tuesday. Welcome everybody to Torque and Drag Tuesday for the Learn It, Turn It, Burn It, Torque and Drag mini series. Today is episode number 3. So excited to have everybody here with you. Today's episode is brought to you by DTech. So if you have not, go check these guys out. Really, you should. DTechDrilling.com. So happy to have them on as a sponsor. They were even sponsored one of my very first conferences I held, which was the Rotary Steerable event. What was it? Push it, point it, rotate it. Absolutely amazing event. That was actually my record for most people watching in real time. I think we hit over like 800. So hopefully we can beat that today. So if you would, like, share, subscribe, tag one of your friends in the comment section. Tag your colleague, tag an enemy, doesn't matter. Tag somebody in the comment section, let them know, if they're in the drilling industry, you should probably be watching this series. We've had lots of great feedback through the first couple of weeks of this. Multiple operators watching and telling their, entire drilling staff, like, hey, you need to watch all of these. One company in particular enforced that all junior engineers had to watch. So really excited about that, to be able to put something out there worthwhile to the industry. Gives you that nice little warm feeling inside, even though it's kind of cold and rainy outside here today. So if you guys would, please let me know where you're watching from. Love to be able to give everybody a shout out. Let's see where we got some people watching from. The comments are starting to roll in. We've got somebody tuned in from Houston, Texas. Thank you for being here. LinkedIn user is always the #1 fan of the show. I tell you what, they are always here, and I am very happy with that. So, Edberto? Yeah, Edberto. Tuned in from Colombia. Thank you for being here. International show today. And Yerevan from, what is that, Calcutta, India? I need to make a trip over to India at some point in time. Mr. John DeWart, tuned in from Colorado. Thank you for being here, sir. We do appreciate it. Robert Carrington and the guys over at Vibration Technology, they've got some really cool technology. If you haven't checked them out, you should. Mark Anderson tuning in from Conroe. Thank you for being here, sir. Zaid tuning in from Algeria. Once again from Algeria. Mahmoud tuning in from Australia. Bob Godbolt tuning in from Rankin Road in H-Town. Speaking of which, Bob set me up last week with Cruise and kids us. Last week was on the Vitor Locksmith show. We talked about whipstocks. Absolute masterclass. I learned so much. What an episode to go back and watch. So if you can't, go back and watch it. Florian tuning in from Austria. I've got a LinkedIn message I need to respond to, Florian. Give me a minute. I promise I will. Marco tuning in from Denver. All right, holding it down in UAE, Dubai, as per normal. He's like our go-to guy in the Middle East. He's always tuning in. Thanks for being here. I'm just going to butcher your name, but initials AKA tuned in from North Dakota. Thanks for being here, man. Appreciate it. John tuned in from Laredo. Miso Randy on YouTube. All right. Nothing wrong. Hey, everybody that's tuned in on YouTube, thanks for being here. Tim Morton. All right. Tim did find it. Made a couple of posts comments this morning. Make sure that he could find it today. So glad you were here. Debbie, who's going to be on episode number 7. We thought that was going to be the ultimate episode or the last episode, but actually, Brandon Foster's coming back for episode number 8. I got to get all the fingers up there. There we go. We'll be back for episode number 8, which will be the wrap-up episode. So if you have any questions left over, come back for that one. And episode number 1 was a barn burner with Brandon. And if you know Brandon and his style, he's very funny and it's very entertaining. So definitely worth being there. Luis from Germany, thanks for being here. Saeed tuned in from India. Eric from south of France. Brian from Bowbridge. Horacio from Argentina. Chris Webb from San Antonio. Hamid tuned in from Austin. Thanks for being here. Cohen, good evening from rainy Saudi. Those aren't 2 words you usually see together. Morning from the Rockies. Jose Ramos tuned in from Katy, Texas. And what's up, everybody from India? Well, Kartik, thanks for being here. We do appreciate it. Today, the day with Dr. C, and we're going to be learning about some basic physics. But first, we need to give away a drill bit. There we go. Comment, and you're going to get yourself one of these big, giant drill bits. YouTube link. We will get the YouTube. I'll post the YouTube link in the comment section in just a second. Let me see if we can throw away this. Get rid of this drill bit here. It's weighing me down. All right, so if you will, type in hashtag DTech into the comment section now, right? And you're going to get yourself one of these fancy drill bits, right? Our sponsor's DTech, dtechdrilling.com, right? Where was that back at? There it is. Yeah, so hashtag DTech into the comment section. Do that. Check out their website and watch this really cool video that we did with them.
DTech's an independent rotary steerable company. We've been around since 2015-ish, right, in one way or another. Started as just an independent R&D company trying to prove it, and have progressed to a fully commercial rotary steerable tool that covers everything from 5 7/8 all the way up to 17.5-inch hole. It's grown tremendously. We're in 13 countries now, operating off and on, obviously consistently in U.S. land, but in the Middle East now as well. So something we're pretty proud of, and the development of the tool. And we're a small team, but growing. And our number one goal is, reliability with customer service, making sure that the customers have what they need. It works to what they expect every time. And our goal, really, because all we do is rotary steerable, is just continual improvement. So every run we use to get better, and we try to just continue to push the performance and reliability envelope.
Just check and see. All right. Somebody said in the comment section there about bad sound quality. I completely didn't realize that my microphone was pinned to my back. It was on my little cord wrapped around my back. So you guys can't see that. I've got these little fancy things. So thank you. I appreciate that. Right? Like, some people might be like, oh, well, I don't want to be the rude person. No, you're being very helpful. If we do not get feedback in this industry, then we don't get better. So there I am, looking like an amateur. Thank you guys all for pushing in. DTech, look at this. Boom, DTech. I'm trying to go up. Should have gone the other direction. There we go. Thank you guys all. We do appreciate that. DTech does as well. All right. So let's do the quick. Well, we still got some rolling in here. We'll give it a 5-second countdown. 5, 4, 3, 2, 1. We've had 40 people put in. Let's see if anybody else gets that to 41. Anybody? 5, 4, 3, 2, 1. All right, we're drawing it. There we go. Who's going to be the lucky winner of one of the giant Gibson reports? Oh, they did get to 41 just in time. Who's going to win themselves? Anirban? You just won yourself a giant drill bit, sir. I'm not sure. I think you commented on where you were, but we'll definitely look at it. Send me a LinkedIn message with your address, and we will get that shipped over to you ASAP. So special thanks to DTech for being our sponsor of the show. All right, today's Basic Physics with Dr. C. We're going to learn some stuff. Be ready to take some notes. Go back and watch episodes 1 and 2. Here we go. Dr. C, thank you for being here, sir. Second time live streaming with me, and I completely believe that this is going to be another awesome video. You were on mute, sir, I think. Oh,
microphone was muted. Now it's supposed to be okay.
Yes, now we're ready to go.
Yes, and that's the proof we are live and we are not an AI, whatever type of chat. I decided from now on to make mistakes when I wrote my post, just to make sure that people understand I'm not a bot, like I was accused some times ago on that. So yes, first of all, this idea of mini series, I think it's fantastic. A great mix of industry and academia in trying to, the way I like to say it, to make an autopsy of, torque and drag, and something that when you drill a well, actually torque and drag is the killer of everything that happens there. Will generate problems, will generate also good results if you know how to play with it. And I did my best today to fill my slides with equations, something I usually do for my students, but now let's hope that your audience will survive on that one. I don't know how many people you have right now live. Let's see how many you're going to have in half an hour and then in an hour after I will show all my slides on that. But that's, I think, something really amazing happening, and I'm glad to be here.
Well, Darcy, thank you for being here. I do have one quick question we've got to answer that we've already got. So if you guys have any questions, be sure to ask them as we're going through. I have a little thing where I can star them, right? So that we can go back and answer them kind of in order. And the more context you can kind of give to your question, don't make it too long because it doesn't show up on the screen the whole way, right? But any little context, you could say, slide 3 or, something like that, just to be able to give us a little bit of context. Saeed, to be able to answer your question, you can go back and watch the series. So we are streaming live on YouTube, Facebook, and on LinkedIn on all 3 at the same time. If you go back and watch any of these, right, you'll be able to see the comments on that particular platform. So we really don't get anything from Facebook. So if you go back and watch there, you're not going to see any of the comments. YouTube, we do get some. LinkedIn's where we get the most. So there is a link in a special feature or whatever on my LinkedIn profile. So you can go back there and be able to watch there, right? So if you go to my LinkedIn profile, right, click the notification bell, then you get notified of when we go live for all of these and future ones. Click to follow so to make sure you don't get those. But you can go back and watch on LinkedIn and on YouTube. Gibson Reports on either one. Should be able to find them. A little bit internet searching, not too difficult. All right, that was important. Next question is, yes, if you have questions, put them in there. All right. Darcy, it is your turn. Let's put this back up there because we do have sponsors and we got to give them some love. All right. Thank you, D-Tech. All right. We'll put your PowerPoint presentation up there. Darcy, I will let you take it from there.
Thank you, David. So first of all, to everybody, including David, in case I suddenly disappear, there was a winter storm announced here in Norman. So it could be that, there will be power outage or internet will disappear. I have nothing against you guys. Doesn't matter what question you say. Doesn't matter how much you're going to critique my presentation today. Is because of the winter storm here in Norman on that. So we finally start to have a winter here. So I cannot start my presentation without bringing something that actually I have noticed in the past 2 episodes of this Torque and Drag mini-series. And this was about some names that has been mentioned several times. I would like to here to address, in memoriam, of course, to Professor Hans-Wolfgang Wold. He passed away in 2017. But his name was probably mentioned more than 10 times in the past 2 presentations because most of the work that has been intensively done on Torque and Drag was happening under his supervision, and he published some of this paper. And also I lost somebody very dear to me, my professor Vlad Olmanu. And the reason they are in my presentation today is because I had, the privilege and the chance to work with both of them. And one thing that happens from both of them is something that I will gonna present in really what follows from here, mainly friction. What I have learned and what I have seen here in this Torque and Drag is that friction seems to be understood as the main problem and main challenge and main solution. But in the same time, I'm a professor. I'm in academia, so let's go to basics. Let's talk a little bit this friction, and I will try. And I know industry sometimes doesn't like this kind of very academic classification. I will try to put these definitions and so on in the proper order for that. Later, I will move on some Torque and Drag basics. That's what we were talking about. I will bring some, I took some notes during the past presentation, like low side, Torque and Drag, Capstan Effect, and probably there will be more in here that I noticed through your comments online. And then I will try to kind of transfer my stuff, my basic torque and drag, to something that you're gonna notice and will happen in our presenter next time, which will be about more about the models, the simulation works, and so on. Something that in an academic environment we don't really do so detailed, but I will try to make a smooth transition to my next speaker. The one will take this from me for next week. So let's look at friction. Friction is typically the frictional force resisting to the motion of two surfaces in contact to normal force pressing the two surfaces together. And of course, I took this from one of the famous, dictionaries that you have it, online. But what is very important on friction is that we do have friction when we try to move. So as long as between the two surfaces there is no tendency to move, friction doesn't exist. And that's a very important definition of that one. Everybody really agrees with, but I wanted to make sure that now at this point, it is on my slides written accordingly to that. So friction is a dynamic process, and normally the dynamic process and everything under the friction will be defined as coefficient of friction, which is, a coefficient that really tries to make a relationship between the frictional forces and the forces that are necessary to move that object. With this in mind, if we look at friction factor, you will find a lot of papers referring to friction factor as being confused with coefficient of friction. And I cannot stop as academia to try to explain you friction factor in most of the engineering is normally defined as the coefficient of friction of an actual value divided by the coefficient of friction of a known value. So very simple and very, very often used in oil and gas is when we talk about friction factor of different thread dopes or lubricants used for tool joints, for drill pipes, casing, tubing, and so on. In that one, the friction factor is defined as the coefficient of friction of the dope that you just bought or you want to use divided by 0.08, where the 0.08 is what API has originally defined as being the magic number of friction coefficient that you're supposed to use. Also, if you want to have a much easier similarity, think about the specific density, where you take the density of a material, you divide it by the density of water, and instead of using, large numbers, you are using a very small number, typically very close to 1, which allows you, to remember typically much easier and to play a little bit with that. So this here, I really want to make sure that whenever you look at the friction, you understand that you have a coefficient of friction, which is a number that can be lower than 1, and then you have a friction factor, which is a number that can be whatever. And that's actually the very important aspect in what we're going to talk in our presentation here about the coefficient of friction. So coefficient of friction is always less than 1, which means that whatever you do, normally you expect that the friction force will be less than the normal force to that particular surface, whereas in the friction factor, you will expect to have a value that is either lower than 1, bigger than 1. Actually, there is no really specification on that one. Let's have a look on this table. It's taken from Rabat, and then it was posted in 2010 by Samuel. And you can see here that a lot of materials has been tested, and tested like one materials against the same material or one material against other materials. And with one exception, which is the aluminum, is defined as having a coefficient of friction above 1. Which is something else, and I will talk in a few slides about that. But all the others, they have really relatively high values. We talk about somewhere between 0.1 to almost 0.61, as I said, except the aluminum. What also will happen is that a lot of scientists will always define the friction in the starting mode and sliding mode things that, again, we're going to talk in the next slides on here. So why we talk about static when actually the friction is a dynamic process? So we have to move the body, the object, in order to create friction. Well, the static refers actually to the, let's say, value of the friction coefficient that happens at the moment, the very first moment you try to move your object. Once the object is now moving with, let's say, constant acceleration and so on, we can call it in sliding, and that will be a different value on that one. So at this point, we're going to come back to this slide, or actually to the table with the values in a different form, later. But at this point, let's look at the friction laws. And we discussed about these friction laws in the past two presentations. Obviously, I cannot skip it in my presentation, and I'm pretty sure you're going to see them for the next 10 presentation that will happen here. But the idea here is that we all agree that friction force is directly proportional to the applied load. The applied load that we talk about, that normally we define it as a normal force, which is the force that happens normally or perpendicular to the forces in contact. The second one says the friction does not depend on the contact area. But here is very important to talk about what scientifically will become apparent area. Apparent area is not the real area that the two bodies may have. Is actually the area that really comes in contact between these two bodies, and I will talk about that too. And last but not least, the kinetic friction is typically considered to be independent of the sliding velocity. This is something that a lot of people are arguing, and mainly is that the theory here with kinetic friction being independent of sliding velocity typically comes from the dry friction. So that means there is nothing in between the two objects. But in reality, we always have something there on this. So with this, three laws in mind, let's go a little bit to the real world. The first one says the friction force is directly proportional to the applied load. But now we have to keep in mind that the applied load or the normal force is not always just the weight of the object. It can be the weight of the object plus whatever other forces will act on that object. So in this case, as you can see here, I put a force F with red, which will push down the object. So in this case, my normal force will increase with that value. And as such, now the normal force is higher. So the friction force between the left picture and the right picture in this case will vary very much. So there will be higher friction force on the right versus the picture on the left. This has a very important impact on the torque and drag calculations. Why? Because in torque and drag calculation, if you are able to estimate the contact points of your drill string with a weld bow, and you are able to calculate now the normal forces in every point, that will show you actually a big difference between a very simplified system. We have talked a little bit about soft and stiff string models, and the main difference will be the ability to identify these normal forces, the magnitude of these normal forces, and because all forces are vectors, so we have to identify also the directions it goes on that. I mean, my drawing here is very simple. We are in 2D, the gravity goes down, the normal force goes up. But imagine in a 3D complex well, we have a lot of complexity in determining the vectors and so on. Don't worry, I promise I will not go too much in detail with those vectors in a full 3D on that, because I'm pretty sure there will be something in the next presentation. So once again, even if we know that friction force is directly proportional with the applied load, do not forget that applied load is not only the weight of the system, it is actually a mix of the weight plus any other forces that may act on that. And those forces, in torque and drag needs to be really estimated. The second thing is, and I really love this, actually, I had my last class, I don't know if some of you have followed me on LinkedIn, but I'm teaching a course which is called oil country tubular goods at the university. And one of the project for last semester was talking about the friction between casing and the wellbore when we run casing. And you can see here two pictures. The top one is the classical that we use mostly in academia, but I believe also for training courses to estimate what is the friction force in a in a well by plotting the weight of a casing in a horizontal well and then estimating the friction force. However, if that pipe will have connections or centralizers or anything else which will impede the pipe to have a perfect contact with the wellbore, then the contact between the new system will happen as you can see here. Let me grab my pointer. And I think you can see my pointer now. So this is now the point of contact, which will be the centralizers or the coupling. And in this case, now the entire weight of the pipe will be distributed half on the other one and half on the other one. I just assume that everything is perfect. Of course, nothing is perfect downhole. But in this case, the friction force will be now the sum of the normal force 1, which is half of the weight, and the normal force 2, which is another half of the weight. So in a real world, the friction force in the scenario from the bottom picture is the same as the friction force in the upper scenario. But in reality, it could be that only a portion of the weight of this small element will go on the normal force N2, and another portion of the element will go on the normal force N1. So that means that by having different forces, these different forces may generate different contact area. And for that, we have to go to a famous physician that came out with the idea of contact stress. That means that the surface between two bodies is actually not the mathematical contact surface, is actually something that happens because at the contact point, there will be a deformation of the two bodies, resulting actually in a much larger area. So let's have a look on, and this will be your first quiz. So what is the contact area of a spherical body, a ball, and a flat surface with no deformation? So the surface is so strong that there will be no deformation as shown in here. Can any one of you tell me on that? Let's do a quiz. Maybe David will give you tons of bits if you answer the quiz. What is the contact area between a spherical body and a perfect flat surface?
We're on a 30-second delay, so it might take
yes, I'm waiting.
Minute. Oh, we've gotten 3 in so far. A single point, a point. Oops. Point.
Yes, a point, but the area of a point is exactly 0. So, in other words, if I will have a perfect spherical object with a perfect, flat surface, the contact area will become 0. So in that case, I will have actually, in terms of stress, an infinite value of the stress, which obviously is impossible in real world. So that's why Mr. Hertz came with a solution saying, okay, that very high stress contact, the surface will deform, and as a result of the deformation, there will be an area which is more than 0 in this case. So that means that the stress at the contact point will be a finite value. So let's go a little bit back here. So what that means to me is that if I do have a softer material compared to a harder material, so let's say a hard rubber with a soft rubber, then what I will expect is that the contact area between the two elements may change. And as a result, because of the contact area that will change, there will be a different friction situation. That friction situation now will not be changed because of the area itself, is because the fact that the softer rubber will create now, will allow a more deepening of the sphere. As you can see here, the sphere will go deeper inside of the rubber compared to the hard rubber, which you're going to go less. We're going to talk a little bit more about this phenomenon in the next slide, where I will show you a much, let's call it intimate contact between two this. So let's go to the next real world. Kinetic friction is independent of sliding velocity. Fantastic. But then you'll see here, and these are just some of the scientific papers that I have reviewed in the past, and look at that. A lot of new models, particularly for torque calculation, are trying now to include the velocity, as you can notice in this equation here. So we have the friction coefficient dynamic with the static friction coefficient, and as you can see here, there will be the velocity included in there, because they have identified that sliding velocity may affect the system. But more than that, the moment between the two surfaces we have anything else than air, so we are moving into wet or lubricated friction, that velocity will play a much greater role. And that much greater role will be very important for understanding the torque and drag in real wells. Because in real wells, we do have mud. We do have a lot of additives we add to the mud. These additives could be lubricants. Friction reducers will be called by a lot of us. But also, we can have elements which will change the friction from, for example, from sliding to rolling. And that's very important. I remember there was a very nice paper where the adding of microspheres of granite or marble into the drilling mud have shown a massive reduction of friction in some wells. Pretty interesting work on that. So the world of friction, it's complicated. So we do have dry friction, and dry friction, in my opinion, does not happen in your well unless you drill with no mud. But even if you drill with no mud, you'll still have some humidity there. You have cuttings, you have a lot of other stuff. So dry friction is more laboratory. So you come to my lab, I will show you how dry friction works. It doesn't work in the reality. In the reality, we always have wet or lubricated. So the reason I call it wet is that if you have water, a lot of people believe that water is not a lubricant. Believe me, depending on the conditions, water is a great lubricant. And you may ask, where is water the best lubricant? Well, if you have rubber and steel, water will be the best lubricant you will ever have for the system. Then we talk about static friction, and as I told you already, static friction happens at the beginning of the motion before your object is starting to move. And then the dynamic, and you see here in the brackets, kinetic or sliding. Our industry is always fantastic in changing the names. So the kinetic sliding friction happens when already the two objects are in relative motion of each other and they are moving. Last but not least, not necessarily very strong accepted in our industry. However, if you look at the companies building downhole components, particularly downhole motors, downhole, let's say, bearings, and everything that rotates within each other, we do have hydrodynamic friction. So in the hydrodynamic friction, actually, between the two surfaces, you always have a fluid. It can be your drilling mud. It can be some other liquid form of other lubricants that you are putting in between. And actually, what happened is that when one part is start to rotate or to move, you are actually keeping in between the gap between these two elements just that fluid, which actually compensate for and reduce fantastic the friction inside. Not to forget is the rolling friction, and rolling friction becomes fantastically interesting when we talk about completion of wells, when we talk about running specialized centralizers, which have inside of them rollers or any other elements that actually will allow the system to rotate, to move when you run the casing inside. I have seen from a lot of companies claiming that by the use of your rolling centralizers, for example, you are able to reduce the friction with almost 5 times. In the extreme cases, one of the example was reducing friction from 0.25 to almost 0.08 or 0.06, which is a very big reduction of friction, allowing you, to achieve better well completion and longer wells for this completion. So this world of friction now tells you one story. Whenever you do torque and drag, you need to do the torque and drag at 2 levels. There will be level 1 torque and drag as part of when you start moving, and then the torque and drag after moving. So you have a kind of a jump in this torque and drag in your situation. There was a small glitch in my screens around here. I hope that I'm still live. I'm just checking, but yeah, it looks like I'm live. I have another computer with me on LinkedIn.
You're still good.
Okay, thank you. So let's look now much more intimate to our friction. So first of all, if there is no motion, friction force is 0. There is nothing that you're going to see here. We are in a kind of lockdown, and the lockdown is not the lockdown from 2020, but it's another lockdown where now, if you look at this surface, you're going to find out that every surface we have has a certain roughness. The quality of the surface, the shine of the surface, the smaller the roughness, but that roughness exists. It's just a matter of how much you magnify that. So let's assume that I put my, professor glasses, and now I can magnify this to the level where you can see the roughness between these two surfaces. So this will be now my zoom. So you can see here, I'm not moving, so nothing happens in here. These two surfaces will kind of stick together. Typically, if the weight or the force pushing down is very big, some of these surfaces will highly flatten itself. They will deform. We suffer local stress deformations that will be induced here. So let's move now to the point where I'm trying to move my system. And in order to be able to move my object, I have first to overcome these points of contact that happens at the micro level between the two surfaces. And you can see here with my fantastic animation. I know you've never seen animation like this quality before, but you can see here in the green circles, that's where we are trying to overcome that. So this is friction. This is where friction happens, and the reason why friction happens. So at this point, once I break this, I'm moving from the static friction to dynamic friction. So if I continue moving, the friction becomes now dynamic in the right term of this picture. So for this one, I can very simple write, and as I told you, in typical friction definitions, we consider that the acceleration is 0. And by that, I can write that the force F is equal to the friction force. And then it has been demonstrated that friction force is proportional with the normal force, and as such, we have the full definition of the friction force. So I'm going to move from here to the next part to talk about the difference between actually friction and sticking, because sticking is a very, very important aspect we have in the well. The sticking is actually a phenomenon where attraction forces between whatever color is here in between the roughness of my steel plate, let's say clay, it's an attraction between these elements and the other surface. So because of the attraction forces, the sticking actually will generate an apparent value of your friction which is higher than 1. So whenever you see in a well that your value of friction is higher than 1, is no friction anymore. You have something else. Sticking could be one of it. There is another phenomenon I will show you in the next slide, but that's where the sticking happens. And I have performed a very, very intensive testing on sticking, particularly when you do corings. Coring in different materials is very important to lead to extraction of a long core the quality or the coring efficiency being defined as the length of the core versus the maximum possible length of the core. In this case, if the sticking of the material to the system exists, you will find out that your torque will increase fantastically high and will affect entire system downhole. In case of the other materials that we have, sticking can be aggressive. Clays are pretty much one of it, but also we have some medium type of sticking on here. If we look to the next one is I like to call it shear, but imagine that you have an object as the one shown, in the lower part, the one that is now moving back and forth. And you are trying to overcome this, let's call it a macro tortuosity you have in the well. Whenever you try to move that one, because the object is much more rigid than you expect, that object will try now to shear to correct the well bore. And this is not anymore friction. This is actually a mechanical work that you spend in the well in order to destroy the rock, to break the rock, and allow the object to move. Why I'm talking about this is that a lot of time, we are trying to adjust the friction coefficients in the hole by performing a mini, back and forth movement of the string or rotating of the string and so on, in order to understand how the friction works in the well. And then whatever you see at the top drive values, you try to put that in your model, and that's the way you do, calibration of your friction factors. But do not forget that in a real well, you don't have the friction you see on top. The friction that actually allows you to find out what is the coefficient of friction. In the real world also, you are shearing, you are crashing the well bore because the well bore quality is not perfect. And it has been discussed a little bit about tortuosity and micro-tortuosity that in the well and the effects of that. That's actually the effect of the micro-tortuosity. We do have this issue that happens there. So be careful that whenever you are in the real well, you do have what is shown here, sticking, you do have shear, and of course we have friction. So with this in mind, let's try to move a little bit more to the classical definition of friction. And the classical definition of friction is, as you can see here, static and dynamic friction. So normally you need to move the object to reach a certain velocity. That velocity will lead you to what we'll call it a breakaway zone. And the breakaway zone is the point between the static friction and dynamic friction. And as you can see here in this graphic, I just used the standard definition where the friction coefficient will be constant, independent of velocity after that. In reality, it's a little curvy, but important is that, as you can see here, the velocity is not perfect zero. In order to reach the point where the static friction moves to dynamic, you need to reach a little bit of motion to that one. It's an elastic phenomenon because if you remember my fantastic animation here with the green dots, you need first to move the roughness contact points, and you need to break that roughness. So you really need to move to have a displacement in order to achieve your real dynamic friction for the system. So these are most of the models that we all agree, and that implemented in a lot of models, and almost any software we have today, they will have their own, let's say, adjustment of the Coulomb friction model, which will be inside. Keep in mind that this will happen, typically symmetric. A lot of people consider to be symmetric. So that means that if you move to the right or you move to the left, the system will be just with a vector. But it will be symmetric in the shape. I found out that depending on the surfaces, especially if two surfaces have been already moved in one direction, when you suddenly change the direction, the friction may be slightly different, at least for a while on that. So that's kind of very important here. I cannot stop talking about another way to look at friction. And this is one of the oldest bit torque model, highly intensively used in a lot of application, where, as you can see here, the torque is friction, which is defined as a function of rotation of the bit, and then multiply with the weight on bit, diameter of the bit divided by 3. But in here, if we look at the classical graphic that will represent the friction for the bit torque, you will notice that is above 1. And inevitably, it has to be above 1 because bit will have to shear the rock. So we'll have to really, if it's a drag bit, classical, PDC bit, will have to shear to the rock. So therefore, the effort that we do is not only to overcome the friction, but also to destroy the rock. So it's an additional extra energy in our system. So with this in mind, I will not really call this a coefficient of friction. I like the way that the original authors have defined this as a friction factor. Unfortunately, they are still using the mu as a number. I will call this whatever, but not mu for this. But it is a different, level of friction in this case. So let's go to the friction coefficient values and how do they look like. So the next quiz is here for everybody, and I know I have 10 seconds to look around. So guys, is 0.75 an acceptable coefficient of friction for your well calibration model? Yes, no will be more than enough in your room. So shall I use this for calibrations? Okay, it seems high. Some of you said no. Great. How about 0.65? No, okay. Well, 0.65 is actually a friction coefficient that you will find it between some materials in the wellbore. But let's move to 0.5. Acceptable? Okay, so now we are going closer to some ranges, and you see here, these are some values I got from the drilling manual, where they say, okay, in an open hole, you expect to have somewhere between 0.15 to 0.3. If you switch to oil-based mud, 0.15 to 0.25. I don't really agree with that. I've been testing in the past oil-based muds, and actually, I found much lower value for oil-based mud in the system. What I can agree is that most of the laboratory tests have shown much lower values than the field test. But the reason, again, is if we go back several slides in my presentation, you will notice that downhole, you do have sticking and you do have shear, which will alter your overall values for that. But also, these are some other values that I have found. This is Gaynor et al. 2001, friction factors, they call it. It's a coefficient of friction, but taken from over 100 wells. And you can see here that most of the values are literally below 0.3 in average. So we are really low values for that. Which, this is, in my opinion, is where we have to look at, because if you test a steel against the rock in a laboratory environment, you will going to get values which are actually typically lower than 0.25 in most of the cases. There are very few cases where you will get higher friction coefficient in any laboratory that you have for that one. So now we all agree higher friction coefficients are a no-no. But now think about and be honest, how many times you had to go to a higher value just in order to match what you measure from the well, because seeing from the well some higher values, you have to do two things. Either you say, okay, this is an anomaly, I'm going to discard this portion and I will try to find something else, or okay, I'm going to have to find a match value just to keep in that. So there were a lot of discussion about these values, and for that. So somebody is, I think, is asking about this, what is coefficient of friction or friction factor. So my numbers here, and I think also the numbers on this table are coefficient of frictions. However, as I mentioned, in our industry, a lot of time, there is a small confusion between friction factor and coefficient of frictions. They are just assuming to be the same. When we talk about what happens downhole, we don't really have a value to compare with. As I said, for dopes or used for drill collars, drill pipes, and casings, we typically have a reference value, it is 0.08, and the friction factor will always be referred to that. In downhole values, we don't really have that reference value. So to my understanding, everything that is reported in any paper that has been published so far, whether they are talking about friction factor or coefficient of friction in the well bore, open hole, or case hole, we talk all the time about coefficient of frictions. So everything you see here, these are coefficient of frictions. So this is something very interesting, because if we really want to now dissect the friction factor, so we want to find out what is, the reason that the friction factor creates so much trouble. So Teodoriu had to spend 19 slides to talk about, actually I have more than 19, but 19 slides to talk about friction factor in torque and drag. Well, the reason for that is actually because friction factor depends on almost everything you have downhole. Is wellbore stability, fluid properties, deflection technology, formation type, hole cleaning, and of course the properties of the materials in contact. A lot of things will create your troubles downhole. But important is to learn about that and to solve the problem. For example, hole cleaning. We know that the more cuttings you have in the wellbore, the more friction you have. So just make something with the cuttings. We know that drilling fluid properties, like adding additives, will enhance the properties related to friction. So let's do some enhancement on all these properties. So at this point, let's go to calculating torque and drag. And the classical theory of torque and drag, these are the slides I have, received from Mr. Yufkam World when I start teaching my first class at Texas A&M. And he was so kind, he said, okay, this is what you have to teach, and you teach it. For your information, I start teaching at Texas A&M somewhere in the middle of the semester, co-teaching the course with Dr. Yufkam World. And he was so happy to dump on me all the torque and drag. So at that point, if we look here, this is a piece of our drill string. We chop it, we put it downhole, and we work on that. And on this piece of drill string now, we have our tension in the drill string that is pulling down is normal, is generated by the weight of the object, which is acting along the wellbore. And then on the other side, we have the tension plus the incremental increase of that tension on the wellbore. Important here, we look at the inclination, one of the main important factor that is inevitably critical to address the torque and drag in wellbores for that one. So the equations are pretty simple. We assume that the acceleration is 0, so that means we can do a very simple force, equation on that. So the sum of forces along the wellbore is 0. The sum of forces perpendicular to the wellbore is 0, and that allows us to define the increase of tension will be, of course, proportional with the weight and cosinus of inclination, and the normal force will be now the weight sinus of our inclination in this case. Typically, we consider this equation as being valid for when you rotate the pipe, because a lot of time rotating pipe means that you are in a dynamic low value of friction coefficient. So friction in this case is, as an assumption, is no friction at all in the system. Now, when the friction happens, we really need to move the string. So the string has to move, in this case, lowering the pipe. So the friction force will have to oppose the motion, because friction force is a kind of, the opposition in our torque and drag, parliamentarian system. So friction always oppose everyone there on that one. And then, of course, when we raise the pipe, if we go to the raising, you're going to notice the friction will go in the opposite direction on that. So once we learn that the friction exists, now we can write the same type of frictional forces for that. And you can notice here that the change of the tension will become now the weight cosinus inclination plus minus friction force. Once again, friction force now has to be treated as a vector. So if the friction opposes the motion, depending on the direction you go, the friction force will be adding to the tension or will decrease the tension, which is very important that whenever we do in a calibration field, the friction coefficient calibration, we do this in both directions. So we are lowering the string, we are raising the string. So we look on both directions, and that will give us a much better, accurate way to measure the friction coefficient for our system. And as you can notice here, I believe a lot of you have pointed about that typically friction coefficient in the well bore has to be between 0.15, 0.4. I got the same from You've Come World long time ago. It's pretty his legacy on that. So he knows what he's doing. So now, again, I try to write the same equation once again. For the lowering, we have to keep negative. So when we lower the string at the surface, it will look like the hook load will decrease, because the friction force is kind of opposing the weight of the system. When we raise the string, when we trip out, the friction force will be very bad for the whole process, because the friction force will add weight to our system and will increase the system. So here is a very classical example that I believe almost every petroleum engineer in this world have had this in his classes. It's about what is the maximum hole angle or inclination angle that can be logged without the aid of drill pipe, coil tubing, or other tubulars. In other words, is a free fall of the tool. So assuming that you forgot to set your slips correctly and your drill string will free fall in the well bore, the question is, what is the well bore inclination where your tool will stop? And I know this happens a lot of time in our industry. So let's look at that one. So in this case, we assume that the tension or the increase of tension in our logging tool, which means the wire line, is 0. And for that one, we know that in this case, the weight or the force that is moving the tool downwards is supposed to be equal to the friction force. You can see here I put a value of 0.4 for the friction coefficient, and then from here we can easily calculate the inclination of the well bore. In other words, if you are dropping things in the well bore, the higher the friction coefficient, the better. Obviously, that will be not good for drilling and for torque and drag, but at least if you don't keep your well bore clean and you keeping dropping tools in the well bore, make sure that they will stay better for you. So with this kind of inclination, this will apply to bottom well assembly. So that means that actually in a horizontal well, the bottom well assembly will never push on your bit, and we know that. So that's why in order to create some weight on bit on a horizontal well, we need to push the whole string downhole. Something that in a classical vertical well theory from 1950s, you'll be told don't do that because you are buckling the string. So let's go to the next one. Basics of equations for horizontal wells. Horizontal well, if we assume that we have just a simple pipe, the pipe sits on the well bore. That's the classical, soft string model. We have the weight on the pipe. The normal is a force is equal to the weight of the pipe. So we can easily write that the force to move the pipe is friction multiplied with the weight. I put here some numbers just for getting some ideas on that. And the torque will be now classical mu, so friction coefficient multiplied with the weight, which will be the normal force, multiply now the diameter, and I divide it by 24 because typically we are using foot-pounds for the units, and is a unit conversion. But what is actually important in here, I will show you in the next slide, is that whenever you rotate the pipe, because of the friction we have in the well bore, the drill pipe or drill collar or whatever rotates in the well will tend to climb on the wall. So instead of having a contact here at the bottom, we're going to have a climbing on the wall for the system. And because of that, normally and accurately, we need to correct this with the cosinus of phi, which will be shown in here. And this cosinus of phi, needs this correction according to the system. Some authors, for example, have also included now the fact that we are in motion. So we have omega divided by the velocity, slip velocity for the system. So you create another equation here. Samuel in 2010 actually introduced a much more complex equation where actually here we are talking about the dog leg, we are talking about the sinus theta as an average, and that will be like a 3D model for this complexity. So this angle becomes even more complex for our system. So with all of this in mind, it means that if you look at, simulation on model A versus model B, model C, and so on, you will find out that the accuracy of these models actually depends very much in the equation they are using it and how these equations are actually interpreting, for example, torque. Torque is very important on that because torque will generate a lot of further, calculation in the well. Next but not least, we have to talk about the Capstan effect, or if you want to, the effect of tension in the drill pipes in combination with the fact that the well bore is curved. And in this case, notice here, we have the net side load that will act on that one. So the tension in the pipe will inevitably change the normal force. If you remember, normal force is not only the weight of that object, but is also the sum of any other forces that will act on the object. So in this case, for the model on the right, the force on the pipe will increase the normal force by creating now normal force, which will be equal to the 2 times the tension in the object. As you can see here, I totally neglecting the weight of the pipe for this case. So new models will start now to add to the torque and drag these side load effects. So you need to have a model which is capable to identify the contact points, and you need models that are able to calculate the forces in these contact points in order to generate this. So in other words, now that I know that the tension in the system has an implication to the magnitude of my normal force, I have to include this. And the standard theory, the very basic theory, will be discussing the effect of dog legs to this theory. And these are the very simple equations, the basic equations, where in this case, as you can notice here, we have to use the tension, the T, plus delta T as an increase of or a change of the normal force on that one. So my normal force here can be more or less accepted as being, the weight acting on the pipe plus, in this case, the tension acting on the system, and we have to take in account the dog leg. Now, when my dog leg is a 3D dog leg, and there are several models, Adnoy, Samuel, and some other authors have come with various 3D models for that one. The complexity of the model is even high, but obviously I cannot disclose to you all the secrets of the simulators on the market because I may not survive too long at this point. So with all these calculations now, the key factors for creating an accurate model is to divide your entire drill string in shorter pieces, and to calculate for these shorter pieces your contact points, and creating these calculations, so that in the end you are coming now with a normal force, which is a combination of the weight of the system plus the tension in the system that will take place for that. So now once we add the friction, you will notice here that the friction in the system will alter the incremental increase of the tension in the system. So when you start from the bottom to the top, you're going to change this incremental friction to the tension, and the result of that, you will now have a much accurate model for your torque and drag. Do not forget, we have the sign here, minus, and there will be another one with plus, because this will happen depending when you are raising the pipe and you are lowering the pipe. Actually, some authors right now are even including a vectorial tendency for torque calculation, where they are considering the fact that your pipe is moving, so that's the vector 1, and the pipe is rotating, so you have a second vector, and by combining these two vectors, you are actually working on this combination of the systems. So that will be the 2D model, and as I said, 3D model takes in account the whole real part of the well, and we'll calculate that. In order to have that, you need first of all to have an accurate wellbore path description. You need to have real-time measurements sometimes, and accurate measurements. Actually, I found a paper recently that they were saying that particularly in the horizontal wells, most of the wells are really off from the predicting path. And there is a big debate right now on the market about the accuracy of drilling horizontal well, in particularly in the survey accuracy of that. Some other analytical equations look like that. As I said, we can talk probably for the next 3 weeks if you want me to go through every single system, but this is another model, a little bit more complex in here, that I found out that tons of them outside for this. But also, let me come back a little bit to my friction factors. I love friction factors, friction coefficients, and you can notice here, this is a classical table. El Jibali et al., for example, they said that they've been using this. It's a classical Excel sheet that allow them to calibrate some field data with their calculations. And you notice here is written friction factor. In my opinion, is still the coefficient of friction on that one. But the idea here is that whenever you do this type of calculation, whenever you work with them, you are using different numbers in order to get some let's say adjustments that look like what you have, what you see in the reality, and these adjustments require you to play with a lot of factors. So academically speaking, what we do in our research group, for example, is that we create a pool of these friction coefficients, and then we let the system crunching a lot of these models with for example, more statistical approaches, and trying to find a better link between this friction coefficient. What, however, I can tell you is that the moment you are deepening the well, the more you drill the well, your friction coefficient change. Your friction coefficient is also a function of the section. If you are inside of your casing, you are having a different coefficient that when you are in the open hole, depending on the size of your open hole, depending on whether the open hole is enlarged or not. Oops.
You all right?
Yes, I saw you talking, and I thought that I lost you. Am
No.
I still live?
Yeah.
Okay, sorry. You're on my other screen, and I thought I lost you. So I was saying that typically the wellbore should be divided in sections that you easily can define friction in that section, and you should actually have variable coefficient of friction along the wellbore. That's actually the most accurate approach that you can have it. How you get this coefficient of frictions, how you apply that, I believe you're going to see in several of my on the next speakers that will come with different models that they are able to do. So this brings me a little bit more to what a better, more complex model will help you to do. So this is from Stefan. I'm pretty sure Stefan will be next week, if I'm not mistaken. So Stefan had a nice software that actually allows you to have a very accurate deformation of your string. You can now create contact points along the string, for example, where you have your stabilizers or whenever your drill string will touch the wellbore. And you can see here the classical model, the one I teach in my class, which is very simple, very inaccurate, but easy to understand the friction in that case. With these two in mind, let's go a little bit more. I don't know how much time I have, but I will try to look at the side forces. Side forces happen in the wellbore because of two things. Number one, you see it in here, is because the well path is not vertical. We have a deviated directional well. The side forces will have an impact on this, and that's why we have side forces. The second one, I don't have a picture here, and I didn't know whether I should talk too much in my presentation about that, but the second one is buckling. Buckling will create side forces independent of where the well is. If it's horizontal or vertical, in both location, you're going to have side forces because of the buckling. So the two major models that you'll find it as part of the softwares on the market are the soft string, where typically whole drill string is modeled as a cable. So therefore, the cable will always lay on the wellbore. And then we have the stiff string. The stiff string typically is the one where you add stiffness to the drill string. Particularly, you have different stiffness for the bottom well assembly versus your drill pipes, and you create now contact points which are not uniform as the soft string, and it's in contact points. Now you can play with that. Of course, there are some mixed approaches on that, but I think this is there were some questions last time about the main differences, and actually I found from Stefan a very nice slide showing how the soft string calculation or solution looks like, where typically you divide or you put the entire contact points along the connectors, the tool joints or casing connections versus the stiff string, which will have now much more contact points, vectorial contact points. As you can see here, they are moving along the wellbore, and obviously the accuracy could be improved. Now, thinking about the accuracy of knowing the coefficient of friction is probably 10% in the best cases in the well. Most likely, most of the softwares will be within 5 to 10% in accuracy or prediction of what happens there. I found here very nice data. This was from a master thesis, I think, from Turkey. I really don't know how to pronounce the name of this guy, but it is online, so you can download it if you search his name. And what everybody is doing is you take a torque value, you take the actual torque value, and then you try to create your torque model. And as you can see here, you put your values like friction coefficient of 0.3, and then you adjust it to 0.25, and you look at that. But the reality shows that actually your torque is much way different than that. Why do you think is this happening? Why the torque looks like that, whereas your pure calculation shows a very straightforward torque? Once again, is because number one, you are trying to use one value for the entire system, which in my opinion is wrong. And I think that probably the next generation of torque and drag simulations will try to come with a much more complex coefficient of friction distribution in the wellbore. I would call it local coefficient of frictions. They could really improve that. And then, second is, don't forget, we have sticking, we have shear in the wellbore elements that are not necessary described by the standard equation of torque, where you say the torque is a function of friction coefficient multiplied with the normal force and a sort of arm-like diameter of the pipe and so on. So that's one of the things that I've seen. Friction adjustments are one of the most important part of our life, and particularly when we are in the field, when you work in the field, you need to spend some or to pay more attention to this. But let's talk about why do we have friction in a vertical well. So you can see here in a vertical well, the weight of the pipe goes, vertical. There is no normal force. My normal force is 0, but still we do have friction in a well. So I know 10 seconds delay. I'm waiting for you to tell me, why do we have friction in a vertical well? I'm just watching on my other screen your answer, so just to know that. Well, somebody mentioned side forces, but we don't have side forces. As you can see here, we have a 0 normal force on that. Where are the side forces coming from? Well, wells are not straight. I agree. Most of the wells have a degree of dog legs. But even if we have a perfectly vertical well, we should not forget that we have buckling. Especially if your vertical well will still lead to a horizontal section, so you have to push down your entire system. The buckling of your string is actually the key reason why the friction will exist even in a vertical well, and cannot be better depicted by my laboratory. So this is a picture from my I will call it, and I'm very proud of that, the largest stick slip laboratory in the world, where you can see how actually a normal string happens when you have torque at the bottom. The string starts to spiral itself. It's a, let's say, it's not necessarily a full buckling, but it's a spiraling because of the string in the well bore. And you can see here from Stefan drill scan simulation showing again the buckling of the string and all these side forces, contact forces in the vertical well, which adds to you this friction in a vertical well. So very important, friction may exist all the time, even if you may not necessarily see at the beginning where the normal force is coming, because normal force is not only generated by the weight of the string, but also by the other side forces that may take place into the system. So I don't know, I think everybody have seen my beautiful video here. So this is the one on the left. Is not an animation, it's a real video of our stick slip simulator. And let's go to the next one. Let's burn it a little bit. What happens when we have friction? I mean, that's the motto of David here. Burn it, let's burn it a little bit. When you have friction, we have heat. And the classical equation to describe heat is that you have the friction force multiplied with velocity, and that will give you sort of friction into the system. That friction creates heat, and that heat can be so high that sometimes your tool joints will really change the color. Have you seen that? I bet yes, you see. And with this friction in mind, well, typically you can calculate this, and the equation above require a lot of assumption. As my students have mentioned in one of their presentation, these are some assumptions that they have mentioned at that time. So we can calculate that friction. It's not easy. It's not straightforward. There is another theory. This is Rabinovich, 1982, who came with a much more complex equation here. I really don't want to go in this equation, but this equation at least can allow you to kind of estimate the rise of temperature when you have friction between two components, assuming that you take the assumptions on the previous slide: no heat transfer, no convection, no heat partitions, and so on. But this is possible to do that. So you can see that torque and drag is not only important for you allowing to run and move your string in and out of the well, but actually if you are neglecting the friction in the well bore, you may end up with heating up your entire elements. And because friction happens locally, friction will affect only one small portion of your string. You are not heating up the whole string. That will be perfect because the heat will be uniformly distributed. But unfortunately, the heat from friction happens locally on the contact point. And that means that you can overheat just one coupling. You can overheat just one tool joint. And that may lead to a total destruction of that element. So be careful. Do not overestimate or underestimate your friction in the system for that. So friction, however, matters more in torque and drag analysis because you have to understand also vibrations. I'm trying to find out why my animation, my video is not working. I believe I need to wait a little bit. Let's be patient, patient, patient. No. Okay. Yeah. Okay. Now it's moving. So you can see here high RPM, low RPM. The friction at low RPM actually seems to be having a higher effect on my entire drill string. So this is another video from our largest drill string setup in the world, which is available at my laboratory. And if you are interested, you are welcome to message me, and I can make a live session for you guys, and we can play with some of these elements. Of course, you can also contact David, and David will make a live session where I will be live in the live session of Live David online on that. So this is now, you can see that friction may cause a lot of dynamics, friction in the system. And Azar and Samuel 2007 have presented here, for example, that erratic torque values may be visible, which are caused by torsional dynamics. And this has nothing to do with the friction per se in the well bore, but is actually backwards. So the friction creates high torque. The high torque creates now stick slip. Stick slip will start imposing torsional dynamics. So vibration actually are highly important for torque and drag understanding is highly important in order to identify vibrations and mitigate vibrations. Typically, the more friction we have, we can talk about a lot of vibration arresting. So the vibration will be attenuated by the friction in the well bore. However, if the magnitude of this friction is really not understood, you may end up with creating more torsional dynamics into the system. And that's why there is a very strong relationship between torque and drag and vibrations. If you remember, and you'll find this online, there is a live session with me and David talking about vibrations downhole. How we reduce torque and drag after we learn everything about friction coefficient? Yes, reduce friction coefficient. Or try to change the contact parts. So instead of having a contact between your drill pipe and the well bore, try to make the contact between the drill pipe and a rotating protector. So you are moving between surfaces which are known, like rubber to steel. Much better friction coefficient, lower friction coefficient than this. Also, drill smooth. Control tortuosity, control micro tortuosity. I think our sponsor will tell you that using, a rotary steerable system with, special, design components and software, you will be able to minimize or eliminate a lot of tortuosity components which are creating high friction into the well bore. And that's something that we work on here. Also, try to make your string to be a little bit lighter. So we need stiff stuff or rigid elements, but lighter elements ideally will be casing drilling casing drilling is a string where it's very rigid but very light, and that could help a lot with the friction. Casing drilling have been also been described as reducing friction in wells. There are a lot of key factors behind that. Why we use the RSS and consider for that one? So I'm pointing here two things: continuous rotation and controlling microtortuosity. Let's see on your side, and I know 10 seconds until you're gonna ask. Why do you think RSS will be the one that will reduce friction in a well compared to any other tools? Any ideas? I don't want to brag. Maybe our sponsor will give you some prizes if you come up with some fantastic ideas on that. Why do you think RSS is the one that will be the best to reduce friction in a wellbore? Yes, dog legs. So we talk about the macro tortuosity, the big aspect of tortuosity. Dog legs are very important. Excellent, high RPM. So this is something very, very interesting on RSS. So there is a very nice tendency right now to move in RSS with higher RPMs for that. The high RPM is not so good for the drill string in the curve section, but high RPM on RSS actually helps you a lot on reducing friction. So that's fantastic. Hanging the weight, excellent on that. Yeah, I think we cover more than my 2 points here on that. Let's go a little bit further. So that's what a typical torque and drag looks like. And here is keep moving. The main criteria of having better, let's say, friction into the wellbore is to keep moving. We talk already about RSS, on rotation, continuous rotation, but also another tool that is highly on the market is the agitator, single dual agitator system. The idea of agitator is that they create a micro motion on the two parts. That micro motion means that your system is shifting from a true static to a, let's call it quasi dynamic friction, and that will enhance your ability to go down and drill the wellbore. You can also see here clear that if you look at the measure depth by having your better systems, you're gonna enhance your or reduce your hook load, and obviously will gonna also help you to reach or achieve deeper sections or longer horizontal section on the well. I think we are almost there for the end, but I remember that somebody was talking about completions. Well, in torque and drag for completion, the equations will be the same. It's just that you have different elements. You have a casing, you have a tubing or a wire line that goes into the system that you have to now reconsider the equations to be applied for that one. But especially when you work with large pipes like casing, a stiff model is really needed. You cannot use a soft model for casing for that. Casing centralizers may change the apparent friction coefficient, so be careful that now you don't have the same friction as you expect on that. There are a lot of components happening there, so you need to do a lot of equations on that. And casing coupling are not phase hardened, so don't forget that a lot of phase hardening friction coefficients may not apply for the casing on that. Of course, we can talk a lot about completion, but I believe there will be some more discussions in the future on that. I just wanted to, to show that I have an idea about these two on this. And Complication. I love this sentence. It's taken from Zhu et al. They published a paper in 2014, and they said that based on nonlinear coupling vibration of drill string, three-dimensional nonlinear dynamic model and dynamic friction torque model were established in highly deviated well with mite drilling using the finite element method to study the vibration rule of dynamic drag and friction torque of drill string in rotary drilling. I mean, this sentence says everything about how complex or how complicated you want to do it. But it is not always about complication. It's about making a model to work. And this is something that I'm pretty sure you're going to see in next week. The detailed models, which sometimes will allow you to create digital twins. They have to work. They have to be reliable to provide you same results over and over again, and to provide you some numbers or some data that are really usable for us in real world in the field. And to do that, we need to rely on some of the most strongest models on the market. I've presented this not because Stefan will present next week, and I know Stefan very well, but DrillScan is one of the software that I've been using it also myself. I'm a little bit comfortable to have this, thanks to DrillScan and of course Helmerich and Payne. We have this software available for our students in our lab, and I'm very grateful for that. Thank you again, Helmerich and Payne, for supporting our laboratory. This is all about that. It's 9:30. If David wants me to talk another 3 hours, I will do it. But I believe there were a lot of questions in the chat, and I will be more than happy now to take over the questions. David, you can take the lead for that.
All right. Well, thank you so much for the presentation. Tons to learn and great interaction from the audience. Thank you guys all so much for participating and essentially answering the questions from the professor. Little pop quizzes every now and then. All right, so let me jump in here. And so this is one of the first questions that we had come up. Is 0.08 same for even premium Cs? And I think we were talking about friction factors or coefficients of
friction.
Sorry,
no. David, coefficient of friction, please.
Sorry.
So yes, so the 0.08 is the value that API has recommended in one of his older standards as being the ideal value for the coefficient of friction inside of a tool joint when you are using an API defined thread compound, or a dope, the way we like to call it. This value is adjusted now for every thread compound you buy with so-called friction factor, where you divide the coefficient of friction of that compound to the 0.08. It has nothing to do with the friction coefficient inside of a well bore, where we have different values for that, but that 0.08 is indeed the coefficient of friction recommended by API for any thread compound used in oil business.
All right. Next, Eric asks, do you expect hard rubber to have a higher or lower friction factor than soft rubber?
Well, so because of the surface deformation, whenever you look at the friction force between these two systems, you may notice that in the soft rubber, and assuming that the other component will go inside of that soft rubber, you will notice friction force which will be higher than in case of a hard rubber. But also, don't forget that soft and hard may have also different contact, and we have to look at the intimate contact surfaces, and that will indeed also change the friction. So in my opinion, I think there was a long time ago when I did this type of test. But if you look at cars, the older the tires are in your car, the easy is to start slipping on a metallic surface. So the softer the rubbers are, the less you slip. So the higher friction coefficient will be for soft rubber.
All right. Rawad says, for slide 13, in theoretically perfectly smooth surface, what happens? No static friction difference or something else? so we can throw up.
I'm just trying to go to my slide 13. I mean, it's a long time when I was talking about slide 13. So,
yeah.
Okay. So, now there is no perfectly smooth surface. I mean, in reality, in pure theoretical, whenever the surface, then the two surfaces will come in contact on a perfect two areas, and the second law of friction. There is the friction is independent of the contact area, so it will be the same. That's why actually in reality the second law of friction actually depends highly on the contact stress between the two surfaces, because in a contact stress this roughness will go deeper in the other one, and actually apparently you're going to see a different friction coefficient. But indeed, for a perfect situation, there will be actually a pure constant friction coefficient.
Just want to throw that out there. Jose says, nice presentation. Thank you so much. All right. Back over to the questions. We already did that one, so we need to uncheck that one. All right. Ask. Dr. C, slide 11, which ones defines rotational friction while drilling? Rotating with motor, drilling with RSS.
So which one define rotational friction while drilling? Well, the rotational while drilling will be actually what we call the dynamic or kinetic friction, is because your system rotates. So you are rotating inside of the system, and as such, now you are in a pure dynamic mode. The rolling friction refers actually that between your drill string and the other surface, you have another roller that actually creates a rolling situation on that one. But normally, when you do rotating with motor or drilling with RSS, you are in a dynamic mode. So the friction there is dynamic, and that's why we like to use an RSS, because with an RSS, your system is permanently in dynamic mode. So whenever you start tripping in or tripping out, your system is dynamically. There will be no high friction first and then low friction. There will be just one dynamic friction coefficient all the time.
All right. Sorry. Here's the next one. See if this gets all the way on the screen. There we go. Question. No motion equals no friction force. A body laying on a sloped ramp stays stationary. Gravity cannot pull it down the ramp. Why? Can we say gravity force component along the ramp has not been enough to overcome friction force coming from body and ramp surface? If yes, then the friction force exists even if no motion.
Well, I know, and that's the funny part of the friction, is that in order to have a friction force, you need to have a system in motion. If the system doesn't move, okay, we do have that friction between the elements here, but that friction between the elements is an interlocking. Is like you hold it on location on the interlocking on the components, and that interlocking, we can say that it is not a visible friction force that will act to your system on that one. However, what you are saying here is that actually the system it would like to move, but because now it wants to move, I have the friction force. Keep in mind that my slide here is on a perfectly horizontal surface. That's why I don't have friction. The moment the surface is inclined, I will be in the situation here where my system has a tendency to move, and because the friction force is bigger than the force that is trying to move the object, then the friction force exists. So my assumption that no motion, zero force is on a perfect slide surface when there is no force acting horizontally on the object. I hope I answered the question.
I mean, if it makes sense to me, then it should make sense to them. So,
come on, David.
All right. Road asks a question on slide 17. Through the factor becomes constant with speed. The rotation speed may affect other aspects such as cutting size, temperature, mud flow around. Any literature you know of that build this correlation, if existent?
Well, there are several papers that actually are talking about much more accurate torque at bit equations and correlations, where this equation is slightly improved. I use this because it is the most accepted one, and a lot of let's say models in the computer software are still using this one here. Um, um, you know, um, I think De Tournay, I'm not sure if I'm saying right the name, but this is one of the guy that is typically talking about this. And by the way, we are currently building. We got some amazing sponsor right now. I'm not allowed to tell the names, but they will be in the next LinkedIn post. We are currently building a new setup where specifically we're going to look at this, and we try to see how flat this section will be. So please keep in mind that actually, because of the constant A1 and A2, you can play with them. So this curve can actually look much more different than that. So for example, one model that we are currently using right now, it looks a little bit like this. So it's a slightly different curve on that. But as I said, I will really start with this paper here. And if you look inside, there will be a few more citations of several authors dealing with that.
Excellent. All right, that was a question. I'm gonna pull that one off. Ari and Road are the two that are stealing the Q&A time here. That's okay. Slide 18. If in reality there are factors in aggregate that tend to increase apparent coefficient of friction, why are the actual coefficient of friction values higher than the plan? I believe I'm missing something here.
Well, we need to ask Mr. Gaynor and all the other co-authors that they have in that paper. So I literally took the table from there and tried to show how they've done it here. So actual normally are the values that they measure. Planning is whatever they start initially with, and so. My 2 cents as an academic, I believe that the planning one are based on the laboratory measurements. And as I told you, typically laboratory measurements tend to be a little bit higher than a real one on that. And then, that's something that could be there. It's a nice paper. If you search for Gaynor et al. 2001, you'll find the paper, and it's a nice paper to read.
All right. All right. Rod asks on slide 39, isn't side force technically the normal force we discussed depending on the tension and the dogleg severity? Also buckling, of course, when occurring.
Well, to a 2D system simplification, yes, it could be the normal force. But in the most complex models right now, side forces are now vectorial definitions of vectorial entities. So they may act in a completely different direction on that. And also the side force now includes not only the weight of the system, but also includes all possible other forces that will act on the system, like tension in the drill string and some other forces that could be. One thing that comes very quick to my mind is when you have differential pipe sticking, the side load will be also affected by the pressure in the well bore and will change this.
All right. Okay, just got to keep track of where I'm at here. So LinkedIn user, whoever it may be, thank you for the question. Slide 42, on bottom and off bottom, or on bottom and off bottom torque as a function of weight on bit, breakover torque, impact, viscous coupling, plenty of torque types to talk about. Thoughts?
Oh, yes, I agree. So right now in the most complex models, I've seen that a lot of new models are incorporating, the interaction between drill string and the drilling fluid, the viscous coupling of the system and so on. I would say that in a lot of experiments that I have done, if you try to really use the proper downscaling, viscous components on the torque are typically negligible or within the 5%, which is typically the accuracy you will actually be able to determine your coefficient of friction on that. But that's kind of my answer on here. So of course, the complexity of downhole process of downhole torque and drag is much more than we are able to capture as of 2023 in our models. But with better computers, better models, more scientists, more researcher, we're gonna be able one day to have the perfect twin of whatever happens there. So I need more students. Look at that. More students, more research, more models.
There we go. All right, let's pull that one off. Rawad asks, and Rawad, let me pull this up real quick. He says, "I apologize for the many questions. Do not apologize for asking so many questions. This is the whole reason why we're doing this. We're doing it live so that we can have live interaction between you guys, y'all being the audience, with the expert here, right? Obviously, we all know that I'm not the expert. Dr. C is, and this is why we're putting it on. So if you've got 100 questions, throw them out there, right? So his question is on question slide 44, how much does twist affect buckling?
Well, in a very simple way, twisting initiates buckling. So if twisting exists, and actually what you see here on the video is actually the twisting that has generated this helical shape of my string, and then the moment I apply a little bit of weight, the system was directly moving to helical buckling on that one. So twisting initiates or enhances the existence of helical buckling. So forget about sinusoidal; it doesn't exist anymore the moment you have twisting, and that's the result of that.
Great stuff. All right, let me uncheck that one. So then we have Froylan? Andres. We'll just call him Andres. Andres, thanks. Can you explain again the difference between coefficient of friction and friction factor?
So the coefficient of friction is actually the value we are using in order to define the friction forces inside of our well. So it's a value that can be determined mathematically or experimental, and that's the value for the friction, the coefficient of friction. The friction factor, by default, and that's my engineering in any engineering situation, is defined as the coefficient of friction of the actual value, whatever you are in the actual situation, divided by a reference or a known coefficient of friction. And it's pretty similar to what we are doing when we talked about specific density, right? An object with a specific density equal to 1 has actually the same density as the water, n.33 or 1,000 kilogram per cubic meter. It depends on the unit you are using, but 1 is very easy to memorize. It's very easy to keep. So in this case, for coefficient of friction, that can be any value between 0 and 1, and typically should not be bigger than 1, according to the entire theory of friction. Whereas friction factor can be any value. It can be less than 1. It can be higher than 1. And it's a value that typically moves around 1, but can be any value on that. So friction factor is actually something that we are not really defining it and cannot be used for the friction force calculation. The real coefficient in the friction force calculation, which is, what is that? Not here. Here. This one, this mu here, this is actually coefficient of friction, and that's the way it has been defined.
All right. Oop, already put that one up. So now, Florian, can you please explain again how string OD and 2 mass IOW, stiffness, momentum of inertia, influences A, torque, and B, static torque, and C, stick slip?
Okay, so let's have a look on this slide. I believe it's pretty good to explain that one. So if I have a system which is very stiff, that means that the system will never bend. If we look at the figure below, there will be no contact around here. So the only contact that happens will happen on the, let's say, couplings elements. So this is a very stiff element. So in this case, for a very stiff system like that one, I will be able to really say my contact points will happen at the couplings or connections, and I can do all the calculation. If the element, however, is very heavy, inevitably this element will start hanging. So we're going to get the hanging belly like a tiny pig. And the hanging belly will generate a contact in the middle. So now instead of having only two really clear defined points, I will have another defined point here that will happen somewhere in the middle of the system. When this element now starts rotating, because of the 3D motion, I may still have fixed contact points here that there will be somewhere in the wellbore, but this hanging belly will start now kind of touching the whole wellbore, and this will change completely the entire calculation of your let's say torque and drag in the well, and will require now, like the drill scan is doing, to use this contact forces, and then that's why you have to move to the stiff model. So this is just a disclaimer, guys, for everyone else having amazing software on torque and drag. I do apologize, I do not mention them too much. It's because I have not have them in my lab. I have not used them for my students or for myself to train myself with that. So this is something, if you want to support my students and my classes, feel free to talk to me where I can get some demo of that software. I would love to use them. The moment I know how they work or a little bit what I get out, I will be more than happy to explain more also in my slides and so on.
Well, I think we had the presenters last week, Oleosoft, right? So maybe we can get those guys to hook you guys up with a little bit of their torque and drag software.
Yes, I would love that. And one of the things that my laboratory is currently capable of, we can help you guys to do validation of your models. So I have 3 different setups to model torque and drag and stick slip and vibrations in the lab. We can generate very consistent data, very accurate data on doing that. And you can see the talk that David and we have it last year or so, where we talk about that.
Yep. All right. Next one from LinkedIn user. How is the pad force and wellbore contact that generated from RSS factored into actual drill string friction factor?
Well, I think the sponsor of our class today is a RSS company, right? So they should know better than that. But obviously, the beauty of RSS is that the friction will be kind of accumulated in one single point, which will be the pads. When the pad is 1 foot, we consider for drilling purposes like 1 point. So you can have that friction to be taken into account. But now keep in mind that it depends also whether your RSS is a full rotary system. So that means the whole pads and sleeves, they will rotate while drilling, or we have let's call it stationary. It's never stationary, but a quasi-stationary sleeve, and everything else will rotate inside of that sleeve. So if everything rotates in that sleeve, then we have a much more complex theory than when the system, the sleeve rotates, where in that case, when the sleeve rotates, we just have to add another torque at the sleeve to the torque at the bit. And that's kind of will be, in a simplified form, the way the torque will be added. When we have a stationary sleeve, well, probably we need 3 hours just to come up with some models, but the models will be much more complex on that.
All right. Next one, we'll have to bring this one back up. So Reddy says, how would you accurately calculate local torque for future torque and drag modeling, linear versus actual torque? Slide 42.
Well, first of all, I think that there is a kind of numbers of papers right now on the market which are trying to incorporate very fancy data analytic solutions in order to get a better match. But if you ask me how I will build a new software to do that, the first things I will do, I will forget about one value of friction along the wellbore. I will talk about, distributed sections of friction coefficients along the wellbore, and I will start playing with that one. I will also incorporate the effect of sticking and shear to the outcome of my torque and drag for the system, and I think that will be the best to have it. But not to forget, we have something else. Typically, what we measure as an actual torque is the torque which is measured at the top drive. The frequency of measuring that torque is 1 second. So that means that value is highly, highly averaged and highly chopped. So actually, we don't really see the reality of the torque downhole. So one way, and I know that some companies, I will not name all of them, so I don't want the other ones not talk to me because I never mentioned them, but there are a lot of companies that are trying now to incorporate in the drill string a lot of new sensors for torque and drag that will enable some of this work along the string. We do in our laboratory some research currently. We are trying to identify how many, for example, of these tools will be really required in a drill string in order to have a beautiful, accurate torque, prediction in a well by using multiple sensors down the hole.
All right. Oh, clicking the wrong button. There we go. All right, Eric, could we predict differential sticking by closely following the torque trend?
Yes and no. So first of all, yes, if we do have accurate data, and accurate data means higher sampling frequency, improving your sensors at the top drive. Actually, don't use the top drive to measure the torque. Use real sensors to measure the torque. It could be a torque sub, and I know there are some on the market. It could be another torque sensor which is incorporated in the top drive. I mean, classically, we are using the motor, the electric motor, to get the torque out of that. And in my opinion, that's not accurate enough. So assuming that we have all this accuracy, then what will happen with the differential pipe sticking? The closer we go to a possible differential pipe sticking, obviously the torque will increase. However, let's go one step back. I'm sorry, I'm professor, I have to do that. What are the main four conditions that has to happen simultaneously to have a differential pipe sticking? The conditions to have a differential pipe sticking is that you need to have contact between drill pipe and the wellbore. You need to have overpressure in the wellbore, so overbalance. You need to have a porous permeable zone, and you need to be stationary. So if you are continuously moving, it means that you are measuring the torque, because torque is the response to motion. So you will never see the torque if you don't have motion. It means that actually by rotating, you do not have differential pipe sticking, unless that differential pipe sticking will be extreme, and then you get stuck while rotating. That's crazy. In other words, I believe that the easiest way to detect differential pipe sticking is to use the drag, not the torque. The torque is a very shallow way to see that one, because once you are in motion, you don't have differential pipe sticking, whereas drag will be the one that shows you that you stop now, and then when you start moving, you have a tiny peak, then you stop again, and when you start moving, the peak is increasing, and you stop again, and the peak goes higher, 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 and then there will be a point where you are done, you can't do anything. Rule number one on differential pipe sticking: once you can rotate, continue rotating. So that will not be a direct indication of your differential pipe sticking. But rotation gives you some very good information about friction coefficient downhole, and you can extract that one to eventually estimate the magnitude of your possible differential pipe sticking in the well, because differential pipe sticking is friction. You get differential pipe sticking because the friction force will overcome your capability to pull to move the string. That's all. It's the same what we've done here altogether. It's even worse because we are in static mode. We can't move.
All right. Here we go. Next question. Does the bit walk affect the torque on bit?
Well, that's a very big question. So if the bit walk will generate micro tortuosity, yes. If the bit walk will generate vibrations, which will create more contact points between drill string and the well bore, the answer is yes. If the bit walk looks like the moonwalking of Michael Jackson, I have no idea.
There we go. And just to go back, Eric said, great answer, thanks. And then LinkedIn user says, well explained, differential sticking. So, all right, sorry, I'm getting emails. Got to get stuff out of the way. Here we go. Next one from Adrian says, when back modeling friction factor, coefficient of friction, and the value obtained is greater than 0.5, would you say it is inaccurate?
Well, as I mentioned, we have sticking and shearing in the well bore. What you see there, in order to match your values, is not the true friction. It actually sticking and shearing. So something is wrong in your well bore. So you have to re-estimate what happens there. You can have also wear between your drill pipes and the casing, which creates, tiny wear holes. And there was a great talk last week about that. And in that wear, whenever your drill pipe goes there, you need much more force to move it. That's not pure friction. That's actually, you have to lift the pipe to get it out of the hole. So that's a different reason why you get this coefficient of friction. So if you get that value, what I will do first is I will really move a little bit higher with the string. I will do some reciprocating, trying to ream a little bit the well bore, and then I will try to measure again. That's my 2 cents, the way I will do it on that. And that's the way it will go. You should do it. But also, the key factor right now, if you really want to stay accurate with this, you need to have real-time monitoring. You need to have a lot of data. I know a lot of companies do that. With the more data you get, look at this data, try to compensate this data for identifying why your coefficient of friction is jumping up to 0.5.
All right. Then we got this one. It says, what a great presentation. Well, thank you guys. Appreciate that. All right, back over to the questions. They're still coming in, so it's good. Is it also safer to assume worst case value than adjust from there?
Well, scientifically speaking, extreme values are always taken away. So you like to be more in a mid-range for that. But of course, if we think about API and oil and gas, I would say worst values are always good because at least they tell you what is the strength, what are the forces that you need to pull the string, to move the string. So if you do, for example, a nice well planning and you are using the worst scenario, in that case may indicate that you need a stronger drilling rig. And I've seen a lot of, let's say, situations where the rig was not strong enough to move the string because the assumption of very low coefficient of friction was done, and by that they decide to use a smaller rig than the reality and end up with getting stuck. So I think that it's not bad to use it, but once you drill the well, once you are in the well, try to now adjust these values to much more real value that you can see. So monitoring.
Okay, so Zaid says that may be my thesis subject, gents. Please tell me whatever it was that you're going to write your thesis about, and if you got that idea or whatever from this show, I would be absolutely ecstatic.
Yeah, and don't forget there are royalties associated with that. I will share that with David. David takes 1%. I will take the rest. So.
Not the way I'm making money. Thank you for the presentation and the subsequent explanations. It's also the guy who won the drill bit, so be sure to get in touch with me on LinkedIn so we make sure we can get you that. All right, back over to the questions. Pull that one one off. There we go. Can we identify the drag cause from hook load behavior, micro doglegs, tortuosity, cuttings, or to be precise, overpull? So there was two pieces to that question there.
That's pretty complex, but I think that you can do that assuming you still get more information from your downhole tools. So, for example, if you are using near bit inclination data that will tell you a little bit about micro door legs or micro tortuosity and so on, combining this with the hook load behavior, yes. If you are talking about a Kelly rig where you try to do that, well, after 50 years of experience, you'll probably have a feeling about how that works, but I don't think that will be scientifically enough to explain a young scientist why that works. But the more data you have, I believe that we can have a very nice relationship between hook load and some of these situation downhole.
All right. Back over to live, it says Robert Carrington says thank you. Well, you're very welcome, sir. The guys over at Vibration Technology, great group of guys. By the way, today is brought to you by DTech. So if you guys don't know who DTech is, be sure to let me take that off. Go to their website. Go check them out. Really great group of guys. Really great group. They're actually sponsoring 3 of these episodes, right? So next one, Carlos says, what is the difference between helical and lockup buckling? Is it possible to slide if the string in helical buckling?
Well, let's see if I can really give the answer. So to my understanding, and that's what I teach in my class, I hope I teach it right, lockup buckling is actually when the helical buckling creates side forces which are so high that actually the system cannot move anymore. So basically, you generate contact forces between the well bore and the string that actually you bring the system in a lockup. So there is no more helical buckling that happens, and there is no motion of the system. Now, the helical buckling creates contact between string and well bore and creates a different kind of friction. So helical buckling can exist in a vertical well. So you have friction in a vertical well, which theoretically should not have any side forces, no friction. So yes, the helical buckling may allow you to slide if the friction forces are acceptable, so you can overcome the friction forces. The moment the friction forces will be very high, then obviously the helical buckling will hinder the motion. If you remember the David and the mighty water hose experiment, that's what we have seen there. It was not a helical buckling because the wellbore was missing, but it was a buckling on that one where the hose friction forces was not able to allow the hose to move, but the hose was kind of buckling it into each other.
I'm surprised at how well that experiment worked out for explaining torque and drag.
Well, David, everybody likes water hoses, especially in the summer.
All right. So this is a question from Russell. And I guess at some point my screen refreshed, and so I lost all the questions. So Rowan, thank you so much for bringing up this. It says on slide 28, when the drill pipe climbs up on the wellbore, then drops, is this another reason for torque oscillations other than bit torque and stick slip? So let's add this back in. There we go.
So yes, I agree. Torque oscillation happens because there is a point where the friction or the climbing is not anymore supported by friction, so the drill string will go down. I do not know what you mean by Russell. I took the 2 equations which are here from somewhere.
Oh, Russell's the guy who originally asked the question.
I think okay. So I thought that I have the wrong citation here for that. But yes, I agree. Friction generates vibrations, and a lot of stick slip situation that happens downhole are not necessarily generated by the bit itself. They are generated by the high friction in the wellbore, and a new generation of simulators is highly looking into this, into incorporating friction to the vibrations. I'm proud to work on one of my research on that, thanks to our sponsor.
All right. Next one here from Jonathan. How do non-rotating centralizers slash protectors compare with rolling centralizers slash protectors?
Well, I don't want to kill the entire industry of rolling centralizers, although I do love rolling centralizers. I believe is a magnificent piece of art, and especially being able to put that on hold. But to make it clear, rolling friction is always lower than contact friction or journal bearing. The rotating protectors, let's say non-rotating because the pipe rotates inside, is a journal bearing. The friction there typically is higher than the rolling. So if you really want to achieve the lowest possible value of your coefficient of friction and correspondingly friction forces in the wellbore, rolling centralizers or rolling protectors are really the key of that. And now that's the moment where I will get a lot of samples from all the rolling centralizer companies so I can show that to my students.
All right. What is your opinion on AI physics coupling models? Are those more accurate? Andres, thank you for your question.
Well, David, are you ready for that? Because the moment I'll give this answer, we'll both lose about 90% of our followers on LinkedIn.
Go for it.
Okay. So first of all, in oil and gas, I believe, and particularly drilling, I believe that artificial intelligence doesn't work. Because you need tons of data in order to calibrate, validate a model, and then you need new data to do something else. And in my opinion, the only way to have a validated AI model to be able to work with, you have two things. AI physics, I love that. That's the way to go forward. And a lot of laboratory setups to validate the data that then you can extrapolate to the field in a new well where nobody was there before, when nobody was the point here. Now, coming back to the question, yes, AI physics is the only way you can use AI in drilling applications. And we have to understand that the fact that somebody is tracking your credit card and knows that you buy, I don't know how many packages of cigarettes per week, and then they start sending you advertising on cigarettes. That's one side of how AI works with blind and no physics behind. In oil and gas, we need to have physics. Don't forget, acceleration works all the time. We are on Earth. The acceleration is 9.81 meter per second square. We have to use that number. You cannot invent another acceleration for Earth unless you move on Mars. And of course, we're going to drill on Mars sooner or later. So AI physics is really the way. Thank you for the question. I believe that's the only accurate model. The only way to get accuracy is to have an AI model that whenever you are jumping out of the physics boundary, the model will tell you, I'm not working here. I cannot do anything. Because otherwise you end up with a friction coefficient of 200. And then you just put it in, it's working. I mean, look at the classical history matching of reservoir engineering. I know my reservoir engineer friends, I don't think I have too many online, but those which are still my friends, they understand that in a history matching, you cannot put the porosity of being 99% just to match your history situation on that one. And believe me, I've seen that. 99% porosity, that's a pipe. It's a pipe with a tiny, I don't know, ball inside. So you have to use physics, and physics is the key. You know, I always teach my students that whenever you want to do any data analytics, any artificial intelligence, it doesn't matter the way you do it, first go to the physics, go to the basics, and demonstrate me that your AI model will first stop when I exceed the boundaries of the physics in the wellbore. Otherwise, will not work.
There we go. Next question. To monitor differential sticking, we should monitor inertial maximum torque just after starting rotation after connections?
Yes, but initial maximum torque is pretty much high function of a lot of stuff, including inertia of the system, including friction at the bit, and sticking shearing and all of stuff. So that's why we have to be very careful when we want to use the torque as an indication for differential sticking. In my opinion, differential sticking is very good defined by looking at drag rather than torque. But of course, combining all of this will improve our accuracy all the time. I agree with that.
All right. This one's from LinkedIn. Is it possible to have values of friction factor outside the range generally all models use, as in what defines the range?
Well, if you try to do history matching, if you try to match your reality with your existing model, and in that model being highly simplified, I assume that yes, you're going to have some crazy values. I still remember my first talk with some companies that they were trying to use a 0.8 friction coefficient in the model in order to match something that happens in the well. And I was trying to tell them, I mean, typically 0.8 is close to having welding in the wellbore. I don't think somebody welded the drill string down there. I believe that we have something else. And I mean, you know, for a quick kind of run, in order to try to identify what could happen, what would be, I will not really tell you not to use it. But in my opinion, you know, for realistic, accurate prediction and so on, you really need to look at values. You know, typically I would say below 0.4, 0.5 will be kind of an extreme that I've seen, but is not necessarily a true friction coefficient there for that.
All right. Last couple of questions we got coming in here. In vertical welds, sometimes I have a problem of calibrating torque to actual. Usually software shows very little change from bit torque to surface torque. I have to assume high friction factor or high bit torque.
Well, I think this is the best question for Stefan, because that's what DrillScan is doing. So if you are using the soft string model, the soft string model doesn't really assume in vertical to have actually very big side forces, and as such the resultant you know, torque that will happen there is very low, is under predicted. So you need really to move to a much more complex model where you are adding, for example, dog legs, and you are adding the buckling as well. You know, that will you know, allow you to understand all these contact forces, and the fact that in a vertical well we do have contact forces as well. And that's kind of this slide. That's what actually happens in your well. That's what you are not predicting with your model. So your model is under predicting because it's not accurate enough.
There we go. All right. Next question. It's the last. But rolling ones will help drag more. No? I think we're going back to the centralizers there.
Well, Florian, I don't think that. You know, the test we've done, but it was not on drill pipes, it was on casing. But the test we've done have clearly shown, and we use some data from the field as well, we clearly shown that the rolling centralizers have reduced the friction coefficient from 0.0256 to about 0.08, 0.09. So it was a very clear reduction of that. In the laboratory, it was even more. I think in the laboratory, we achieve a equivalent friction coefficient for the system to be in the range of 0.5. So it was a 5-time reduction of the friction. So rolling centralizers will do that. Yes, I agree that depending on the direction the rollers are made, you may have you know, rolling centralizers in only one direction, and that may change a little bit the drag, as you mentioned. But there are a lot of modern centralizers that actually have rollers in both directions, and they will significantly improve the friction in the wellbore.
All right. Well, I have to say this. Thank you so much, sir. Thank you, Dr. Z. I appreciate you immensely and all of the contributions you've made to our industry. That was actually the last question, because the other last question I had was just a repeat question from before. Somebody put it in twice. So special thanks to D-Tech. Thank you guys so much for sponsoring this. thank you guys all out there for watching. We really, really do appreciate it. It means so much to myself just to be able to see the industry come together, to be able to watch this. It fuels me to be able to continue doing these things and putting them out there for free. I don't think education in our industry should cost as much as it does. So if you guys want, this will be on YouTube, LinkedIn, and Facebook. You can go back and watch all of them. We will be uploading the presentation from today and last week's here pretty shortly. I need to make posts about both of those. Once again, next week, we've got Dr. Stefan Manon from Drill Scan, H&P, right? He's coming on next week to be able to talk about tight clearance weld geometry, capturing micro-tortuosity effects, BHA tendency modeling, and precision standoff. That is next week, January 31st, Tuesday at 8 a.m. And that one is also brought to you by our good friends over at D-Tech. So the week after that, Neil Armstrong. Week after that, Mitch with K&M. Sorry, Neil with Merlin. Mitch Abushin with K&M. Sorry, and then Debbie with she's employed by Landmark. I have to get that right. Technical details there. And so, yes, so we've got, what is it? Applications, special operations, and then operations and in real time. And then finally, once again, with Brandon Foster. So, and then this week on the Vidor Luxman Show, we've got Travis Harris from Alman Tool Company giving us an education on liner hangers and casing. Next week is Ahmad Mayer with Newpark doing drilling fluid myths. The week after that, Kenny Baker and Mike Holcomb to talk about the new generation of floor hands. Tons of content coming up. Guys, please do me a favor. Like, share, subscribe. Follow me on LinkedIn. Click the little notification thing to be able to get updates as to when we're going live with these. Also, just tag somebody in the comment section. I really do appreciate it. Every little bit of help counts. And thank you guys so much. Dr. C, any last words from you, sir?
Well, David, I have a quiz for you. You know what the D in D-Tech stands for? It's your sponsor, so you should know why D from D-Tech stands for.
Drilling, maybe?
No, it stands from no tortuosity, because their rotary steerables will cancel the tortuosity in the well.
All right, then. Well,
thank you, David. Thank you, everybody. Thank you for your questions. Feel free to text me if you feel that my presentation was too outdated, or if you have any questions. I love to answer one-to-one. And if you are interested to see a live streaming of my setup in the lab, talk to David, talk to me. We'll be happy to organize anything you need.
Yeah. I need to make a trip up to Oklahoma, come see the lab.
Yes, you have to bring me the bit, so I'm waiting for that.
All right, guys. Thank you guys so much. Do appreciate it. Tune in next week, 8 a.m. Tune in this week for the Friday Vidor Locksmith Show. And as I always say, know your industry.